So in this video, we'll be doing the May 2024 papers for analysis and approaches. We'll be doing paper 2, Timezone 2 for higher level. So this is a calculator paper, so please have your TIs ready. So let's begin. Number 1, we have functions f and g, and they're defined for x's -1 to 0. And we're given the intersections. Okay, so first we want to find the intersections, and then we want to find the area of the region enclosed by the two graphs. So what we want to do is first we want to graph this on our calculators, and we want to set our windows appropriately. So make sure that we want to show from x's -1 to 0, but we might want to show from maybe like -3 to 1, just so we can kind of zoom out a little bit. So let's put in the two graphs. So we'd have 1 minus x squared, and then we would have e to the power of 2x. And we would set our windows as x goes from maybe -3 and x goes until 1. And instead of like actually picking what our y values would be, we could choose like zoom fit. So you can hit the zoom button, 0 for the zoom fit. But if you do that, sometimes we zoom out too much. So let's just do it manually. So y min, I think -5 would be enough. Y max we'd do 5. And it seems that the x min hasn't been set appropriately. So x min, -3, x max, we'll say it's 1. Okay, so there we go. We have our graph. 1 minus x squared, that's a upside down parabola with our x-intercepts at -1 and 1. So we have something like that as our f of x. For our g of x, we have a exponential function that goes through 0, 1, right? So when x equals 0, both of them are going to be 1. So this is our second piece of graph. Oops. And there is going to be some bound area between where f of x is greater than g of x. So if we were to solve for when a is equal to b, we could just set these two equal to one another, or we could use our calculator's intersection functions. So if our x is from -2 to, say, -0.5, it will give us our intersecting point here. So that would give us -0.91656. So a would be -0.91656. So a would be roughly -0.917. And for b, we can find the other intersection. So if the left bound is like, say, -0.5, and if our right bound is 0.5, we would have our intersection. And that seems to be exactly at 0, 1. So when x is 0. So our b is going to be 0. So this will be our value of a and b. If you want to find the area of the region enclosed by these two, we would have to do integrate from a to b, f of x minus g of x. Because f of x is clearly above g of x at this interval. But we don't have to do this manually. We can use our calculator. So we would just put in integrate from -0.917, which was a, or just to be more precise, we could do 91656 all the way to 0, and we put in our equations for f and g. So we would have 1 minus x squared minus e to the power of 2x dx. So you could do this directly, or you could use your functions. So if you go to your second trace button on your calculator, we have our integration. So our left bound would be -0.91656. And our right bound would be 0. So if you do that, our area turns out to be 0.65. Okay, so the area bound underneath the f of x is going to be 0.65990, and the area bound underneath the g of x is 0.42004. So what we would do is we would just have 0.65990 minus 0.42004. So that's going to be roughly 0.2399, or we would say 0.240. So if you use your calculator or your graphing features, you would get 0.240 as our area bound. Next, let's move on to number 2, where we have linear regression. So we are given a bunch of x data points and y data points, and the calculator can be used to find the line of best fit that best passes through all of these points. So that's y is 2.1875x plus 0.6875. Okay, and the regression line must always pass through the mean point x bar and y bar. So how do we verify that? If x bar is 7, y bar will be 16. Well, we just plug it in, right? So we have our equation, like y bar is going to be 2.1875 times the x bar value, which is 7. And we can add a 0.6875 there, right? So if you solve for that, y would turn out to be 16. So if you go to our calculators, we have 2.1875 times 7 plus 0.6875, and that turns out to be 16, so we just verified part A. Okay, and B, given that Q minus P is equal to 3, what's the value of P and what's the value of Q? Okay, so in order to do this, we actually know what our y bar is, right? So we know that our y mean is going to be 9 plus 13 plus p plus q plus 21 all over 5. So if you add everything up, divide that by the number of data points, that should give us 16, right? So that's going to be 16. And we were given in the problem that q minus p is going to be 3. So we just need to tie these two together and solve the system of equations. So for the first part, we could say p plus q is going to equal 80 minus 21 minus 13 minus 9. So that's going to be 59 minus 22. So that's going to be 37. Okay, so p plus q is going to be 37. And q minus p is going to be 3. So what we could do is we could just like add these two. Then the p's would cancel out. We would get 2q is 40, right? So organizing all that, we would say q is then going to be 20. And since q minus p is 13, we could then say p is going to be 17. Right? So the value of p, value of q, that's going to be 17 and 20 respectively. Okay, so you might have thought we would have to, use our linear regression function, enter this into our spreadsheet, but thankfully it wasn't that question, so we saved a lot of time. We are just given the regression line right away, so we're able to solve this without using the actual linear regression feature on our TI. Okay, so number 3, we have logarithmic models. So sound is often measured on a logarithmic scale. So what that means is if you have like units like decibels, increasing by like 10 decibels doesn't necessarily mean that the sound is 10 times louder. It follows its own logarithmic scale. So we're going to see what that means here. Okay, so let's assume that intensity can be modeled as loudness. So if you put in intensity into our variable I, that would give us a loudness factor, L. So decibels, so intensity, which is measured in some arbitrary units, that would go in the scale of like tens, but the decibels, which is L, that would follow a logarithmic scale. So if we go from like 6 to 7 decibels, that might mean the sound is increasing by 10 times. Okay, so that's like the background here. But all we need to do here is just plug everything into our functions. Okay, so we have S1 having an intensity of 10 to the negative 6 and a loudness of 60. Okay, and S2 has a intensity that's twice that of S1. So let's find the intensity of S2. So, so S2 is simply going to be 2 times 10 to the power of negative 6 units, right? So S2 would just be 2 times 10 to the negative 6. In order to find the loudness of S2, if you want to find L2, we just plug that in to log base 10 and 2 times 10 to the negative 6 times 10 to the 12. So L2 is going to be 10 times log base 10. And we'd have 2 times 10 to the 6. So if we go to our calculators, what does that give us? We go to our math, log base, we have log base 10, and we have 2 times 10 to the 6. Okay. And to that, we would multiply a 10. So that would give us 63.01, or around 63.0 decibels. Yep. So the loudness of S2 would be 63 decibels, where the intensity was 2 times 10 to the negative 6. So part C. This time we have a decibel, so the loudness is given, and we want to solve for intensity, I. So it's like in A and B, we used I to find L, but this time we're trying to find L to find I, right? So let's write down the formula for L and I. So this was 10 times log base 10, and we had I times 10 to the power of 12, right? So this is the formula that was given. And previously we knew what the value of I was, but this time we know what L is. So L is 115, and we're solving in reverse for I. So we have log base 10 and 10 to the power of 12 times I. So first we can divide both sides by 10. So we'd have 11.5 and log base 10, 10 to the power of 12 times I. Okay, now, if we use our knowledge of how a to the power of x is equal to b, so this exponential relationship can be written as log base a b is equal to x. So if you use that, since our base is 10, we have 10 to the power of 11.5 is equal to 10 to the power of 12 times I. So I will now be this divided by this, so we'd have 10 to the power of 11.5 all over 10 to the power of 12. Okay, so this would give us I, the intensity is 10 to the power of negative 0.5. So if you put it in our calculators, 10 to the power of negative 0.5, that should give us 0.316228, so forth. If you round this to 3 sig figs, we would get around 0.316 units. Okay, so there you have it. You have your formula booklet, so you should be able to comfortably switch between logarithms and exponential relationships. If you do all that, our intensity would be 0.316 units. All right, so for number 4, we have a kinematics problem involving the velocity as a function of time. So we have Vt. And what we're trying to do is we're finding the velocity, the maximum velocity, as well as the acceleration. So we might have to plot this function on our graph, and we have to identify some key characteristics, such as the maximum point or minimum point. And we might have to find the differentiation, like v prime t. So let's begin with part A. What is the velocity of the particle when t equals 2? Simple, we just do vt, or v2, right? So we substitute in t equals 2 into this function, so you would just get 1 plus e to the power of minus 2 minus e to the power of negative sign, and we have 2 times 2, which is 4. Okay, so we can use our calculator to do that. You just need to be careful of our mode, because when it comes to putting in inputs like time, we have to make sure that we're dealing with radians, not degrees. Okay, so unless we're dealing with angles explicitly, in all cases, we want our settings to be in radians. So we have 1 plus e to the power of negative 2, and then we have minus e to the power of negative sine 4. Okay, so that would give us negative 0.996 meters per second. And that is our velocity of the particle at t equals 2. Next, we want to find the maximum velocity of the particle. So since we don't know if you're going to be like changing directions, going negative and all that, we would want to check by plotting this first. So we want to have our t from 0 all the way to maybe like 2. So on our calculators, we want to see a bit wider than that. So we want to set our calculators to maybe like negative 0.5 to 3. Okay. And we want to put in the equation for velocity. So we have 1 plus e to the power of negative x, or negative t, minus e to the power of negative sine 2t, or 2x. Okay, so that would be something that looks like that. And we do go to the negative region when t equals 2. So the maximum velocity seems to occur at this point, this peak. And we can use our calculator second trace analyze maximum to find the left bound at 2, our right bound at, so our left bound at t equals 0, our right bound at t equals 2. And that gives us the maximum point at when t is 0.40583 or 406. The velocity will be around 1.18231 meters per second. So our maximum velocity would be 1.18 meters per second. Okay, so that's part B. And we want to find the acceleration of the particle at the instant it changes its direction. So first we calculate when it changes its direction, which is this 0 point. So Vt equals 0 is when we change direction. So if you solve for that, we have second trace 0 and left bound 0. Right bound 2, so we see that our time is 1.658 seconds. And at this point, we have our turning point. So we want to find acceleration when time is 1.658, or when v prime 1.658. Okay. So we could actually do this manually, find our expression for t. So v prime t, so we could actually use our chain rule to find what we get and then plug in 1.658, or we could just use our calculator's function. So second trace number 6, we can find dy over dx directly when our x value is going to be 1.658. So when x is 1.658, we have our 0, and our acceleration, or v prime t, is going to be negative 2.53 meters per second squared. So on our calculators, it allows us to find the dy over dx slope at this 0. Okay. So that's C. So the point is, in our paper 2s, we don't have to manually solve for all of these kinematics equations. What we need to do is just be familiar with plotting these functions as time. And we might have to use a bit of like dy over dx or integral features. Okay. So number 4 is simple, as long as you know how to use your calculator features. Number 5, let's say we have a random variable x that follows a binomial distribution where there's n trials and probability of success 0.25. So for each trial, we're saying that there are 2 outcomes. There might be a success or a failure. So we'll say like success with a probability of 0.25 and failure with a probability of 0.75. Okay, so if we have n trials, we could have like a total outcome of either x being 0, 1, 2, all the way to n, right? So we could have 0 successes out of n, 1 successes out of n2 successes out of n all the way to n. So these are the possible outcomes of having this many successes out of n trials. But we want the case where x is greater than or equal to 1. So what we want is from 1, which is all the possible values of x, we want to subtract x equals 0. Okay, so we want to subtract the probability where x takes 0. And we want that to be greater than 0.99. So before using our calculators, I think we can just use our understanding of binomial events. So if you have x following a binomial distribution where x takes a certain value like small case x, then we can say this is n choose x, and then success probability to the power of x, and the failure probability for the remaining events like n minus x. Right? So in our case, if we say n is unknown but x is 0 and p is 0.25, what we're going to do is we have 1 minus n choose 0, and then we get 0.25 to the power of 0, because we would have 0 successes, and then we would have 0.75 for n trials. So we want this to be greater than 0.99. Okay, and what we also know is n choose 1 is simply going to be 1, because there's only one way to choose nothing out of n. So we would get 1. So we would get 1 minus 0.75 to the power of n. That's going to be greater than 0.99. So you could use your calculator to solve for this expression, or you could say 0.01 is greater than 0.75 to the power of n. So what I would do is I would just do like log base 0.75, 0.01 is equal to n. So if I solve for n, I would know some decimal value, and I would need 1 greater than that, right? So I would have to round up from there. So what you could do is you could go to math log base 0.75 and 0.01. So n turns out to be around 16.007, but it's not good enough that it's equal. We need to have so if you were to like think about this graph right here, a 0.75 to the power of n would be a decreasing like decay function that starts from like 0,1 like that, and 0.01 would be the cutoff point. So n has to be greater than 16.007, so n has to be greater than this. So the least value of n would be 17. So if you have 17 trials, then the probability that x is greater than or equal to 1 is greater than 0.99. Okay. So n would be 17. So that's number 5. Let's move on to 6. So in this one, we have related rates. So remember that we always deal with expressions like dy over dx. So it just means how much does y change relative to x, right, with respect to x. So the volume of a spherical bubble is said to increase at a constant rate of 5 cubic centimeters per second. What that is saying dv over dt is going to equal 5 cubic centimeters per second. And it says the initial volume is 0. So we start with V0 is equal to 0. Okay. And we also have, so we want to find the rate at which the radius is increasing as a function of time. So we might want to know dr over dt. And we want to know when that happens. So the time is when Vt is equal to 20. So we have all these pieces of information. We just got to piece everything together. So the volume of a sphere starts out as 4 over 3 pi r cubed. And if you were to differentiate this with respect to the radius, like dv over dr, that would be 4 pi r squared. And we can also use the fact that if you have dv over dt, that may as well be written as a volume's rate of change with respect to radius times the rate of change of the radius over time. Right? So dv over dt is dv over dr times dr over dt. Okay, so we know that dv over dt was given as 5, dv over dr was given as 4 pi r squared, and we want to know what dr over dt is. Okay, and then we need to know what r is, so we just solve for this one. So we said the current volume is 20. So we should be able to figure out what r is. So r is going to be the third root of 15 over 4 pi, or actually 15 over pi. So if you put that in our calculators, we get 15 divided by pi raised to the power of 1 over 3. So the radius at this moment would be 1.6839 centimeters. So we just got to plug everything into this one right here. Okay, so in order to find dr over dt, we just need to plug in our value of r here into this formula right here. Okay, so we would have 5 equals 4 pi times r squared. That would be somewhere around 1.6839 squared. And we multiply that by dr over dt. So in order to get dr over dt, we would get 5 over 4 pi times 1.6839 squared. Right? And if you were to calculate that using your TI, that would give you 0.140 centimeters per second. Okay. Yep. So just checking, you would go to your TI, put 5 divided by 4 times pi times 1.6839 squared. And we get like 0.14032, so that rounds to 0.140 centimeters per second. So that's what the radius growth rate is. So what you notice is that the radius doesn't really grow at a constant rate. So the volume may be, but if you have a sphere, what you see is earlier on when the sphere is small, right? Like with the same increase in volume, the radius would grow at quite a quick pace, right? So let's say the radius increases by 1 centimeter. But the time taken to grow this by 1 centimeter, that's not the same when the sphere gets larger, right? As the sphere gets larger, in order to achieve the same growth in radius, so if you want to grow this radius by another 1 centimeter, we would need a much greater volume, right? So that's why the rate of growth of the radius over time changes, and we can't really just use constant values. We would have to use this related rates formula, right? So the rate of change of volume over time is equal to the rate of change of volume with respect to the radius times the rate of change of radius with respect to time. So we just need to plug in our knowledge, our known values into here to find the eventual dr over dt. So that's how you would do number 6. We have a curve that's rotated about 360 degrees about the y-axis, and we have a solid of revolution. So in our formula booklets, we know which formula to use, but just to make sure, you should probably trace it out and see if you're revolving it about the x-axis or the y-axis, and you need to educate yourselves on any boundaries that you're trying to revolve this. Okay. So you could go to your calculator and plot in y is 4 ln x minus 2. X minus 2. And our y value is from 0 to 4. And we're revolving about the y-axis. Okay, so you want to draw this out. So Windows from So if you were to plot this on our calculators, I think we get a graph that looks something like this. So when x is 3, y is going to equal 0, and then we have a logarithmic relationship. And when y is 4, x would have to be some value right here. So when y is 4, we have 4 times ln x minus 2. So ln x minus 2 has to be equal to 1. That means x would be 2 plus e. So e being like 2.7, x would be somewhere around like 4.7. So we don't need to know that exactly, just for clarity's sake. We could say it's like 2 plus e, and this is our y. So what we have here is we're trying to revolve this to get a solid that looks like that, right? So we would get like a bunch of conical shapes here. And we're just trying to find the volume of the solid formed. So if you go to your formula booklets, you'll find that it's pi integrate from the boundaries of y. So here it would be 0 to 4. And we would have like a bunch of cylinders. So let's say we have a disk or cylinder where the radius is r. So we have like pi r squared. And then we have like dy. That's like our infinitesimally small thickness. So we would have dy over here, and we have r squared. But what is r? Well, we want it to be the inverse function of f. So for a given value of y, we want to know what the x is, right? So as we go up this stack, we know how this x value or how this radius changes. So we would get f inverse and put in our value of y here. Okay. So if you were revolving this about the x-axis, it would just be f of x dx. But since you're revolving about the y-axis, this is what we need. So you do need to find the inverse function as well. So let's switch about the x and y here. So that would give us x is equal to 4 times ln y minus 2. So that would be x over 4, and then we would get ln y minus 2. Okay. So this further translates into e to the power of x over 4 is equal to y minus 2. So y is e to the power of x over 4 plus 2. So that's what our inverse function is. Okay. So we get pi, integrate from 0 to 4, and we get e to the power of x over 4 plus 2, and then we get dy, right? So if you were to solve this squared. So if you were to do that, that would give us the volume. Okay. So you can go to your math, integration 0 to 4, and you would have e to the power of x over 4 plus 2. This entire thing has to be squared. Right. And we have to multiply a pi here. Okay. So using our calculators, we seem to get a volume of 176.78. And that would be, we don't have the units, so we don't need to write that. So our volume is going to be 176.78. Okay. And all this is testing you on is knowing how to use a formula. V is pi integrate from y1, y2, f inverse y squared. Okay. So you don't need to know how this formula is derived, but in your textbooks or your lecture notes, you might have seen that this comes from the idea of adding infinitesimally many volumes. So we have like very thin cylinders of very gradual thicknesses. So we could have like delta y and pi x squared, right? So this would be the volume of a cylinder. We're adding that for all cylinders where I goes from like 0 to n and n goes to infinity, right? So we kind of start off with this like discrete assumption of we're dividing this solid into countlessly many cylinders of variable radii. But if you divide this into infinitesimally like smaller and smaller sections, that ends up approaching this integration notation, right? So that's the formula that you have to use. And if you did everything correctly, checking your graph for visualization, make sure there's no weird funky shapes going on, then we should find the volume as 176.78. Okay, now let's move on to number 8. We have complex numbers and de Moivre's theorem. So first, we have this complex number z as 1 plus cosine 2 theta plus I sine 2 theta. And we want to show that the argument of z is going to be theta. And we also want to find the modulus of z. That has to equal basically 2 times cosine theta. Okay. So let's start with A first. How we find the argument of z is we just do arctangent of z, right? So let's say, let's talk about the general case. If z is a plus bi, right? So if it's in Cartesian form where there's a real component and an imaginary component, we would find the argument of z. So we would find like argument of z by doing tangent inverse of b over a, right? So what that is because if we have a Argand diagram, we might have like a here and b here. So the argument z we're looking for is this theta, right? Or let's just say this is argument of z. Then the tangent of argument of z is going to be b over a. So if you want to find the argument of z, we just apply the inverse or reverse operation there. So argument z is tangent inverse b over a. So in this case, the argument of z, so for our specific case, argument of z is going to be tangent inverse of sine 2 theta over 1 plus cosine 2 theta. And if we were to work through this using trigonometric identities, then we should get theta. Okay, so that's the premise of number 1. Secondly, if you want to find the modulus of z, we know we just do a squared plus b squared and square root, right? It's just using Pythagoras because modulus is the length of this one, so it's just a squared plus b squared, which is our modulus. So in our case, the modulus of z will simply be 1 plus cosine 2 theta squared plus sine 2 theta squared. Right, and if we were to square root that, that would give us the modulus. Okay. So let's look at the first one. Let's first try to simplify sine 2 theta over 1 plus cosine 2 theta. Right? So let's take note of the idea that cosine 2 theta is basically so if you use this identity, we would get 2 cosine squared theta, right? So we could say this is like cosine squared theta minus sine squared theta. Or we could say this is 2 cosine squared theta minus 1. Right? Because if you recall, sine squared theta plus cosine squared theta is going to equal 1. So if you manipulate that, sine squared is just 1 minus cosine squared. So we could leave off with this expression right here. And that means 1 plus cosine 2 theta is now going to be 2 cosine squared theta. Okay. Furthermore, we know that sine 2 theta, using our double angle formula, is going to be 2 sine theta times cosine theta. So with these identities in mind, we would just have tangent inverse 2 sine theta cosine theta all over cosine squared theta. And if you work that out, we can cancel out one of the cosines. And recall that sine theta over, oh, so this is 2 cosine squared. Yeah, and we can cancel out the 2's, and we would just have sine theta over cosine theta here. So we'd get tangent inverse of tangent theta. So this turns out to be just theta only. Okay. So we just showed that the argument of z is indeed theta. Right? All we had to do was just take the tangent inverse of the imaginary part over the real part, and we introduce some trigonometric identities, and that gives us our identity of theta. Okay. Next, for the modulus, let's try expanding the squareds. So that would give us 1 plus 2 times cosine 2 theta plus cosine squared 2 theta plus sine squared 2 theta. So what we notice here is this can be written as a 1, right? Because sine squared plus cosine squared is just going to be a 1. So we would get square root of 2 plus 2 cosine 2 theta. Right. And what we found out earlier was that if we had 1 plus cosine 2 theta, that would be 2 cosine squared theta. So using that identity once more, we can say this is now 4 cosine squared theta. And performing this square root, we would actually get just 2 cosine theta. So once we have all of these trigonometric identities in place, we can use that for both number 1 and number 2. Okay, so for the show that problems, we just need to arrive at the same conclusions, and we did that by using our basic understanding of modulus and arguments. Okay, so that's it for part A. Let's move on to part B. So hence or otherwise, we want to find the value of theta such that the argument of z squared is equal to the argument of z is equal to the modulus of z cubed. Okay, so this is where de Moivre's theorem would come in handy. So if you have like r times cis theta raised to the power of n, de Moivre's theorem suggests that we could just raise the modulus to the power of n and multiply n to the argument. So we have cis n theta. Okay, so how that applies here is if you have z squared, that's just going to be the modulus squared times cis 2 theta. Okay, so the argument of z squared is simply going to be 2 times the argument of z from earlier. So the argument of z was theta, so this is just going to be 2 theta. So that's like part 1. Part 2, if you have the modulus of z cubed, this is going to be the modulus of z raised to the power of 3, right? So we said that the modulus was 2 cosine theta. So if you raise that to the power of 3, that is going to be 8 cosine cubed theta. So what we want to do is we just want to solve for when 2 theta is equal to 8 cosine cubed theta. And since we have our calculators ready, we could just solve for that. Okay. So when is 2 theta equal to 8 cosine cubed theta? Well, you could just go to your calculator, plot in y equals 2 theta minus 8 cosine cubed theta. And you can just find all the values of theta that make sense, right, when this is a 0. But we do need to take note of the idea that theta is between negative pi over 2 and pi over 2. So we just need to keep that in mind. So first, make sure that we're dealing with radians, not degrees. And second, we want to enter in our formula. So it's 2x minus 8 times cosine x cubed. So if we were to do that, also our x value would be between negative power over 2, so that would be like negative 1.557. Power over 2, that would be 1.57. So let's just set our x min and x max to here. And we want to be able to clearly see the y, so maybe from like negative 3 to 3. So let's plot that. Yep, so we see a bunch of possible candidates for our zeros. In fact, for our interval, there's just one, right? So there seems to be a 0 like all the way in the negative region, like negative 2.7-ish, but what we want to see is the 0 in our interval here. So let's say the left bound is going to be like 0, right bound, let's say it's like 1. So if we were to sketch that, we are able to see this 0, right? So when x is 0.91324, our y is 0, right? If you plot in y1. So the value of theta would have to be 0.913. Right? In that case, the argument of z squared is equal to the modulus of z cubed. And there you have it. That's how you would solve number 8. So it's a revision of de Moivre's theorem and trigonometric identities. We're given a curve that has y equals x minus 4 over ax squared plus bx plus c, and we're trying to find the non-zero constants a, b, and c. So we will try to use the information given to set up a bunch of equations, and we will probably have to solve a system of linear equations to find the value of a, b, and c. So first, let's look at the first piece of info. So the curve has a local minimum point at 2, 1. So the first fact is that it passes x equals 2, y equals 1. So that's our first piece of info. The second one, the vertical asymptote happens when x equals 1. So the vertical asymptote happens when we have something like a non-zero term at the numerator and a 0 at the denominator at x equals 1. So that's our second piece of info. Our third piece of info will be us having a local minimum point at 2, 1. So if you were to somehow find dy over dx, that's going to be 0 when x equals 2. So we have our three pieces of info. We're trying to execute on that, get more specific equations, and after we solve that system of equations, we should be able to get our a, b, and c. So let's first look at number 1. We're going to substitute in x equals 2 and y equals 1. So for the first part, we could say 1 equals 2 minus 4 all over a times 2 squared plus b times 2 plus c. And if you were to simplify this, this should give us 4a plus 2b plus c is equal to minus 2. Right, so we just multiply this denominator onto both sides of the equation, and simplifying, we get 4a plus 2b plus c is minus 2. The second one, we need to know that ax squared plus bx plus c is going to equal 0 when x equals 1. So a times 1 squared plus b times 1 plus c, that's going to be equal to 0. So a plus b plus c equals 0. So that's our second piece of hint. Third piece, we're going to take y prime. So we will have to use the quotient rule. Remember, if we have u over v prime, that's going to be u prime v minus uv prime over v squared. So you get u prime v minus uv prime all over v squared. And that's going to be equal to 0 because we have a minimum point, right, after we put in x equals 2. So if you were to try that, we should get x minus 4 prime times ax squared plus bx plus c minus x minus 4, and then ax squared plus bx plus c prime. Right? Ax squared plus bx plus c prime, and we get this whole thing all over ax squared plus bx plus c squared, and that's going to equal 0. Okay. So the denominator is not going to be 0 because we have non-zero constants of a, b, and c, and x equals 2 here. So we just need to set the numerator as equal to 0, right? So this is our first equation, this is our second equation. The third equation we have is going to be, so this is just going to be 1, and this is just going to be 2ax plus b. So if we were to substitute that in, we get ax squared plus bx plus c, but since x equals 2, we would get 4a plus 2b plus c. And here, let's just put in x equals 2 right away. So we get minus 2 times, this would be 4a plus b. So this has just become minus 2. So we get plus 2, and then we get 4a plus b equals 0. So the third piece of equation we would have, it would be 12a plus 4b plus c equals 0. Okay, so let me just write that all together to tell you which system of equations we need to solve. So we would have 4a plus 2b plus c equals minus 2. Then we get a plus b plus c equals 0. And then we get 12a plus 4b plus c equals 0. So if you were to solve this using our calculator, we should be able to find the value of a, b, and c. So let's head on over to our calculator. We can first go to our matrices. So we can go to second matrix. We can edit our matrix. So we're going to write this in augmented form. So we're going to write something like 4, 2, 1, minus 2. 1, 1, 1, 0, 12, 4, 1, 0. So if you were to take the RREF of this, the reduced row echelon form of this, that should give us the right values of A, B, and C. Okay, so let's put that here. So we have a 3 by 4 matrix in which the entries are 4, 2, 1, minus 2, 1, 1, 1, 0, and 12, 4, 1, 0. So let's put that in. Okay, so we have our matrix A being this one, and we want to put the REF form here. So we can go to our second matrix button, we want to go to our math, and if you go down, there should be reduced row echelon form, or RREF button, and we're going to put in our matrix A. Okay, so if you put that in, it's going to give us a diagonal bunch of like ones here. So we're going to get like 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we get our values of A, B, and C, right? So let's try that. It gives us 3, minus 11, and 8. So that means our solution is A is 3, B is negative 11, C is 8. Okay, so that's your final answer. So what we did here was we got our graph. We had 3 separate pieces of hints, right? So we know that it passes a certain coordinate. We know that it has a local minimum at a certain point. We have a vertical asymptote at a certain point. So we make use of that information to derive the equations we need. And then we solve for that using simultaneous equations or matrices. So that's how you would do number 9. So now over to number 10, we have a PDF equation. So PDF question. So probability density function. The main equations we need to know is if you were to integrate f of x from the entire range. So in this case, the probability density function is just defined for 0.5 to 3. So if you were to integrate this whole thing from 0.5 to 3, we know we should get a 1. We know that if we were to integrate this by multiplying a x to this, that should give us the average or mean value. So that's going to be the mean. If you want to find the mode of x, that's simply going to be the maximum point of f of x, right? So when is f of x the greatest? Well, that's going to be the mode. And if you were to find the median would be somewhere between 0.5 and 3. So if you were to integrate from 0.5 all the way to m, which is the median, that should give us 0.5, right? So where this m is going to be the median. So as with all probability density functions, we will have to use these for integration operations to solve for what we need, right? One of them is just finding the maximum of a function. So first of all, let's just find the mode of x. So you don't need to do any integration here. We just need to find when this will be a maximum. So you could go to your calculator and find this graph, see where this peaks. Okay. So if you were to graph this on our calculator, we want to set our window settings to 0.5 to 3, and we want to make sure the y is fit in accordingly. So let's put in this equation first. So we have 6 over 85 times 4 plus 3x minus x squared. Right? So if we put this equation in from x is around like 0 to 3, we should be able to see the whole graph. So I'm going to get some space and enter it from 0 to 4. Right? So if your y min is set from somewhere around like -1 to 1, I think you should get a clear picture. But if that doesn't work out, we can always adjust it using zoom fit. Okay, so let's see what we get. Okay, so it seems like we have a 4 plus 3x. Okay, so so it seems like we have a function that's generated like this. So from 0.5, it starts at around here, slightly less than 0.4. And we have a peak somewhere around here, and it seems like we reach a y equals 0 at x equals 4, right? Okay, so this is a PDF function that we get. Let's find the maximum point here, because that's going to be our mode. So we go to second trace, find the maximum point. Left bound, we're going to say it's from 0.5. The right bound, we can say it's from 3. Okay, so although this kind of continues like this overall, our function, our PDF, our probability density function just cuts off from 0.5 to 3, right? And our maximum point is here. That's going to be when x equals 1.5. Right? So when x equals 1.5, the PDF y is going to be 0.441. So you just need to include the details of this graph. That should be enough to justify the mode is going to be 1.5. Okay, and once we have this graph, we can further perform like integrations for the following questions. So let's move on to the next one. So this says we're going to find the probability where x is between 1 and 2. So we simply integrate from 1 to 2 f of x, right? So if we were to integrate that, that would give us 85 and 6 and 4 plus 3x minus x squared. Okay, so we can go over to our calculator to find this integration value. So that's going to be, so we can go to, so you can like exit the graph option and hit the math button, and you should be able to find the fn integration button. Right? So you can use like the math feature, and you can go to like fn integration. So we will put in from 1 to 2, and we will put in our expression. So we'd have 6 over 85 times 4 plus 3x minus x squared, close brackets, and that should give us 0.435. So 0.435. So that's going to be the probability that x is between 1 to 2. Right? Next, if you want to find the median, we want to go back to our formula. Say we start from 0.5. If we integrate this to the median, so let's call that like m, integrating this to the median should give us a PDF area of 0.5. Okay, so this equals 0.5 is what we want. Okay. So in this case, I think you might have to use a bit of hand calculations. So what we want here is, if we were to move this to the left, right, so we just want to perform this manually. So we would have 24 over 85 x plus, we have 18 over 85, but we now have x squared. So it would be 9x squared over 85, right? So if you differentiate that, we're going to get 18x over 85. And then the last one, we're going to get x cubed, and we get 2 over 85, right? So if you were to differentiate this, the 3 would become a 2, and the 3 would come forward, so we get the original equation. So the manual integration of this is what we have here. We want to substitute in m and 0.5. So doing this definite integral, that should give us 0.5. Okay. So if you were to plug this in, we could have 24 over 85 times m plus 9 over 85 times m squared minus 2 times m cubed over 85 minus, now if you do x is 0.5, that's going to be 12 over 85. Then we get plus 4, so 0.5, so that's like 0.5 squared, that's like 1 over 4, so it's negative 340 and 9. And then we get 1 over 8, so that's like plus 1 over 340. Okay, so what we did is we put in x cubed, so that's like 1 over 8. So 2 over 85 times 1 over 8, we know that's going to be 1 over 4, so 1 over 340. Okay, so this is going to be 0.5. So we're going to go back to our calculator to solve for what this is. So we get 24 over 85x plus 9 over, so note that x stands for m in this case. So we have 9 over 85 times x squared. Then we get minus 2 over 85, and then we get x cubed. Then we get minus 12 over 85, and minus 9 over 340 plus 1 over 340. So if you were to solve for when x becomes 0, or when, so we want to solve for the value of m here. In our calculator, that's going to be x. When this whole thing becomes 0.5. So we want to find the intersection with 0.5. Okay, so since our median is going to be between 0.5 and 3, we just set our x windows to between 0 and 4. And y min minus 1, y max 1, that should be more than enough to show when they intersect. Okay, so we want to go to second trace intersect. And let's try to find the left bound as 0.5, right bound as 3. The intersection occurs when x is 1.687. So that's our m value. Okay, so when m is 1.687, or when m is around 1.69, we see that that's our median, because integrating from 0.5 to 1.69, that's going to give a net area of 0.5. Okay. All right, so now let's move on to part D, the probability that a randomly selected customer spends at most $48. So if you go back to our original premise of the problem, like x is the variable that represents the weight of chocolate bought, and we have the probability of x being, values between 0.5 and 3. So what we want is, we want to say at most $48 is going to be spent. And so we would have to look at the first case. So the first case is if the customer buys somewhere from more than 0.5 but less than 0.75 kilograms of chocolate. Okay. In that case, the money spent would be 25x. But that would clearly be between, like $12.5 to somewhere around like $18, $19. So that's clearly less than $48. Right? So if the customer is spending more than $48, that means x is somewhere between 0.75 to $3 kilograms. Okay. So in that case, the customer is going to spend 24 times x on chocolate, right? And we want that to be less than 48. So we want the customer to spend less than 2 kilograms, right? So we want him to buy less than 2 kilograms of chocolate so that he buys less than $48 worth. So what we do is we find the probability that x is between 2 and less than 2, right? So we want to integrate from 0.5 to 2 because 0.5 kilograms is like the bare minimum he has to buy, right? So we would do this f of x dx, right? So if you were to use our calculator, we had entered in our we had entered in our equations. So what we do is we integrate from 0.5 to 2. So that would be the probability that he buys from 0.5 to 2 kilograms. Right? So that would give us 0.635, right? So this is the probability that the customer buys between 0.5 to 2 kilograms of chocolate, meaning he spent less than or at most $48. Okay. So this variable price is what makes this question a bit difficult, especially for part E. So let's see why that's so. We're trying to find the expected amount spent per customer. So what we usually do is we could just multiply f of x times x. So that would give us the mean value of how much chocolate the customer would buy. And then we could just multiply the price per chocolate, right? But the thing is, this changes based on the intervals. So from 0.5 to 0.75, it's $25 per kilogram. And then from 0.75 to 3 kilograms, it's $24 per kilogram. So we might have to set up 2 separate integrations. So if we were to find the expected amount of chocolate the customer would buy, that would be from 0.5 to 0.75, and then we would have f of x. Okay, so f of x we saw as 6 over 85 times 4 plus 3x minus x squared. So if you were to multiply another x here, that would give us the amount of chocolate the customer would buy, right? From 0.5 to 0.75. And we would just multiply 25 here, because that's the price per kilogram of chocolate. But then if the customer exceeds 0.75 and goes all the way to 3, then we have a new price, which is 24. Right? So we would add up these expected values, multiply by the price to get the expected amount spent per customer. So we have 4 plus 3x minus x squared, and then we get x dx. So we can now use our calculator to perform this integration. So we can just do from 0.5 to 0.75, and then we multiply 25 here. And then we also have to multiply a x here. And then we add another one. So let's first find that one. So this one is going to be 1.51482. And let's re-enter this again. So we have from $24 per kilogram. So we now have 24. And we integrate from 0.75 to 3. So that should give us 39. So that should give us somewhere around 39. Yep. 39.4428. So if you add that all up, we should get 40.95 or somewhere around $40.96 spent per customer. Okay. So it's a typical expected value problem where we integrate from this entire range and we multiply x times f of x dx. But we do need to take note of how the price changes from the 0.75 kilogram mark. So we just have to do this separately and add it together. So that's how you would do number 10. Right, so let's move on to number 11. We have a sprinkler problem. So we have a sprinkler at point S, and it's shooting its water all around this circle. and we have a straight chord AB. So S is 14 meters from this path. Okay, so this path is a straight line that goes through this radius of the sprinkler. Okay, and first things first, we just need to find that AB is 28.57. So first thing we could do is we could try drawing SB, and since this is a radius, this is also like 20 meters, and this is a shared side, and this being 90 degrees, we have like this RHS condition. So that's like a right triangle. We have right angle, hypotenuse, and a side that's shared. So we can say, like, if you say this is, something like O, we could say ASO is congruent to triangle BSO. So all we gotta do is just find out what this is and multiply 2 to that. So in order to find AB, we would say we're gonna do 2 times the length of square root of 20 squared minus 14 squared. Right? So using Pythagoras, we know AO squared plus 14 squared is 20 squared. So this is what gives out to be the half of length AB. So AB, using our calculators, would then be, we have 20 squared minus 14 squared. So that's going to be 28.5657. Continuing, so AB would roughly round to 28.57. Right? So that's how you would do part A. Now for part B. The sprinkler is rotating at a constant rate of 1 revolution every 16 seconds. So it's important to note, like 1 revolution, that's like 360 degrees or 2 pi radians. So we need to show that it rotates for an angle of pi over 8 radians in 1 second. So yeah, we would just have 2 pi radians is rotated every 16 seconds. So that would just be pi over 8 radians per second that's rotated. Okay, so B is pretty straightforward. C. AB is watered in each revolution. So we want to look at the time when the sprinkler is passing from A to B, right? So we have our point A and then we have our point B. So we know that the sprinkler is going to be rotating around the circle. We want to know like what the angle here is, right? So if we say 2 pi or 360 degrees is like this entirety, for the sprinkler rotating at a constant angle, if you find theta over 2 pi, right, or theta over 360 degrees, that would give the fraction of time it spends watering the path from A to B. Okay. So let's find out what this angle theta is going to be. So based on this diagram here, we just have 20 and 20 and 28.57. So we have 20, 20, 28.57. So we can use cosine rule to find out what theta is going to be. So we could say 28.57 squared is equal to 20 squared plus 20 squared minus 2 times 20 times 20 times cosine theta. And we can solve for what theta is going to be. So we could have 28.57 squared minus 2 times 20 squared. So organizing this one, we'd get 16.2449 all over negative 2 times 20 times 20, so that's like 800. So negative 800. And that should give us cosine theta. So if you're to solve for cosine theta, if you were to solve for theta, we would just do cosine inverse of this value, so 16.2449 all over negative 800. So let's do inverse cosine of that. So negative 16.2449. And we divide that by 800. So that gives us 1.59, or if you were to convert that to degrees, or actually we could say it's in radians. So we could say like theta is 1.591 radians. And what that would give us is, so t would be, it's rotating once every 16 seconds. But since theta is only 1.59 out of 2 pi, t would also be a fraction of 16 seconds. So using the proportionality, so we could have like t, so the ratio from t to 16 seconds is equal to the angle theta and 2 pi radians, right? So if you use that proportionality, you get t as 16 times this divided by 2 pi. So t would be somewhere around 4.05 seconds. Okay? So t is going to be 4.052-ish, or t is roughly 4.05 seconds. So we use cosine rule to find out the angle, and we recognize that the time spent sprinkling along AB is a time spent between angles theta, right, out of 2 pi. So that would give us t as 4.05 seconds. Now let's move on to D. So let's say the sprinkler has 1 clockwise revolution, and at t equals 0, the water is crossing the edge of path A. So this is when t is 0. And t seconds later, it's moved to point D, and the distance is D, like vertically south of A. And we have angles ASD is alpha, and angle SAB is beta. So alpha and beta are shown in this diagram here. So let's write an expression for alpha in terms of t. Okay, so if you want to do that, we just need to look at how t is set up. So we figured that the speed of rotation, so if you were to write something like d theta over dt, or actually let's write d alpha over dt. So we know that the sprinkler is rotating at this constant angular speed of pi over 8 radians per second. Right? So if you want to know what this angle alpha is, all you got to do is just do, we start from 0, and then we do d alpha over dt times time elapsed. So alpha would just be pi over 8 times t. Right? So when t is 0, alpha is going to be 0. If t is, say, like 1 second, alpha would have increased by pi over 8 radians. If t is 2 seconds, it would have increased by 2 pi over 8 radians, such and such. Okay? So d is pretty simple. Alpha is pi over 8 times t. E. It's known that beta is going to be 0.7754, and we want to know how this relationship can be modeled here. Okay, so we want to find the triangle here. Okay, so let's look at this triangle right here. So we're going to draw ASD. So we have A, we have S, this is 20, and we have some movable point D here. And the D is going to be this one. So this is alpha, this is beta, and this is going to be our small d. And d is going to be moving as a function of time, and we want to find that. Okay. So what we could do is we could actually set up a side length here, which is, so let's say, so we can use a sine rule here. So note that this angle is now going to be 180 degrees, or just pi minus alpha plus beta. Right? So we could set up 20 over sine of pi minus alpha plus beta equals d over sine alpha. Right? So we could say alpha is now going to be sine pi over 8 times t, because we established earlier that alpha is pi over 8t. Right, so that's what d is. We know that for sine angles, right, if you have sine pi minus alpha, that's just going to be equal to sine alpha. It's just how it is. if you draw the sine graph, you see that the sine values are the same, whether we have alpha or pi minus alpha. So we could just rewrite this as sine alpha plus beta. Or actually, yeah, this would be alpha plus beta because we'd have a bracket here. Okay. And then we would just still have the 20 here. Okay, and how would we find alpha plus beta? Well, we could do, so let's now find what beta is going to be then. Okay. Oh, and it's known that beta is going to be 0.7754. Okay, so we can actually just put in what 0.7754 is going to be. So what we could do is simply 20. So actually we don't have to change this. What we could do is we could just plug in the value of beta. So this would just be sine pi minus alpha minus 0.7754, right? And if you find that, so if you do pi minus 0.7754, that is 2.366. Okay, so rewriting this, this is 20 over sine 2.366 or 2.37 minus alpha equals d sine pi over 8t. So rearranging everything, we should get d is going to be 20 times sine pi over 8t all over sine 2.37 minus alpha. But instead of alpha, we would just write pi over 8t. So it all just starts from the sine rule, right? Using that side length over the sine of the opposing angle, right? That's going to be constant, and we just fill in our knowledge of beta and alpha. Okay, so we just derived the expected equation here. So that's it for E. Okay, moving on to F. At t equals 0, how far is this turtle from A? Okay, so this turtle is walking along the path. So if we have our sprinkler from S and the turtle is moving from like A to B, I guess we could say like the turtle's position is at D based on the time here. And if we were to say this is the distance of the turtle after time t, this is the expression here, right? So first things first, at t equals 0, the turtle will be g0, which is just 18 meters from A. Okay, so I guess the turtle just starts at like the 18-meter mark. And if you represent the distance between the turtle and point D with W, then we could find W in terms of G and D, right? Okay, so if you were to look at this diagram, the turtle is basically moving somewhere from here along A and B. Okay, so if you want to find the distance W, we would just do W is the position of the turtle minus the distance of point D. Right? And I guess we could put in an absolute sign here. So that's going to be 0.05 t squared plus 1.1 t plus 18. And we would subtract our equation for dt, which was 20 sine pi over 8t all over sine 2.37 minus pi over 8t, right? An absolute value there. So that's our expression for w in terms of t. So I guess we could write that as w as a function of time. So when will the water first reach the turtle? So when will wt equal 0, right? Because d and g, right, the position of the turtle and the position of where the water is sprinkling, they have to be equal. So if we solve for that, we could just do that on our calculator. So we would just put in this entire expression into our calculator and solve for that. So we would have 0.05 x squared plus 1.1 x plus 18 minus 20 times sine pi over 8 So pi t over 8 or pi x over 8. And then we would do divide by sine of 2.37 minus pi t or pi x over 8. Close brackets, close brackets. And we also want to make sure that this is in radians. So we want to make sure that time goes from 0 seconds all the way until maybe, so we could go a few seconds. So let's say time goes from maybe 0 to 20 seconds. And we also want some ample distances, so maybe we'll do like -10 to 30-ish. Okay. And we did use radians, okay. And let me just make sure the brackets are all in place. Okay. Yeah, and if we also have the absolute value sign, everything should be all right. Okay, so the first time this happens will be 0. So let's say the left bound is from 0 and the right bound is from 4. Then this occurs at t is 3.349 seconds, or when t is roughly around 3.35 seconds. So so that's the when. In order to find where the turtle is, we could just do g of 3.35, right? So we just plug that in here. So 3.35 squared times 0.05 plus 1.1 times 3.35 plus 18. So the position of the turtle is going to be like 22.246 or roughly 22.2 meters from A, right? Vertically down from A. So that's when the water would first reach the turtle. All right, so now let's do number 12, where we're doing this differential equation, and we might have to do a lot of like manual calculations, but there's also the numerical way of doing this with Euler's method. Okay, so first things first, we have to use Euler's method with a step length of pi over 12 to find the value of y when x is that. Okay, so remember that in order to get the Euler's method, we get the n plus 1th y by taking the previous value of y, and then we add the step size times dy over dx, right? So it's kind of like having a case where we have like xn and yn. We find the instantaneous slope here, right? Where the slope is like dy over dx. And then we move by step size delta x to xn plus 1. And then we move on until like yn plus 1. Okay. So there's a way of doing this. You would just write our xy and the dy over dx. So initially we have x is pi over 4. And then the next step would be pi over 4 plus pi over 12. So we could say that's going to be around pi over 3. So actually, if you were to write it more conveniently, this would be like 3 pi over 12, 4 pi over 12, and then we would have 5 pi over 12. So we just need to perform Euler's method just for 3 steps. Okay. And y is going to be pi over 4 initially. So we can find what dy over dx is going to be. So dy over dx is y cosecant 2x plus square root of tangent x, right? So dy over dx, that's just going to be pi over 4 times cosecant. I'm just going to write 1 over sine. So 1 over sine times pi over 2. because pi over 4 times 2, that's pi over 2, plus square root of tangent of pi over 4. Okay, and we know that tangent of pi over 4 is going to be 1. You can check that with your calculator. Sine pi over 2 is also going to be 1. So the dy over dx is going to be pi over 4 plus 1. Okay. So that's our first thing. Right? So our dy over dx is pi over 4 plus 1. Our initial x and y values are this. Okay, so when x is pi over 3. Okay, so when x is pi over 3, what's the y value going to be? Well, we would have yn, which would be just pi over 4, plus pi over 4 plus 1 times pi over 12, because that's a step size. So that's going to be pi over 4 plus pi squared over 48 plus pi over 12. So if you were to add all that, we would get these ones would just be 3 pi plus pi over 12, so that's like 4 pi over 12, or just pi over 3. And then we would have to add pi squared over 48. Okay. And then we can find the new dy over dx. Okay, so instead of like doing this all manually, you can now use your calculator to do this. So our dy over dx, that's just going to be y. So I'm going to put in, so I'm going to write pi over 3. And I'm going to add pi squared over 48 there. So that's like 1.25. So our x value is pi over 3. Our y value is 1.2528. Okay, so we're going to use that to find the new dy over dx. So the new dy over dx is simply going to be 1.2528 times cosecant 2 pi over 3 plus square root of tangent pi over 3. Okay, so let's put that in our calculators. 1 over sine 2 pi over 3 plus square root of tangent pi over 3. So our new value of dy over dx is going to be 2.7627. So what you want to do is when x is 5 pi over 12, we want to get our new value of y. So we would have pi over 3 plus pi squared over 48, which was 1.2528, plus pi over 12, that's a step size, times the new slope, 2.7627. So the new y is going to be pi over 12, and then plus 1.2528. So that's going to be like 1.976. So if you were to get this to 3 sig figs, that would give us 1.98. So that's how you would do part A. Okay, so since it's just 3 steps, I think you could manage to do this without the table form, but you could also use a spreadsheet to automate the calculation. So you'd have x, y, dy over dx. X would just go, increasing with pi over 12 at a time. Y, you have our initial value, then you find your dy over dx, and then we continue calculating our new values of y. Okay, so that should give you 1.98. Now on to part B. Let's find dy over dx. So if you were to differentiate 1/2 ln cotangent 2x, cotangent x, that's going to be what's on the right side. Okay, so we could simply use a chain rule. So if you have ln x, differentiating that would give you 1 over x. So here we would just write 1/2 times 1 over cotangent x, and then we'd multiply the chain rule. So we'd have to multiply the differentiation of cotangent x. So that would be negative cosecant squared x. Okay. So that would give us 1 over 2 times cosine x over sine x. And then we'd get negative 1 over sine squared x, right? Oh, but it's 1 over cotangent x, so this would be sine x over cosine x. So we just use the identity that tangent is sine over cosine, cotangent is cosine over sine. So if we do this, we get negative 1 over 2 sine x cosine x. And using the double angle formula, we can further write this as negative 1 over sine of 2x, right? So negative 1 over sine 2x, that may as well be written as negative cosecant 2x. So that is what we have on the right-hand side. Right? So we start from the left-hand side, perform this differentiation. We use our trigonometric identities to get negative cosecant 2x on the right-hand side. Okay, so that's how you would do part B. Okay, now on to part C. We're trying to show that square root of cotangent x is the integrating factor for this differential equation. So let's rewrite the differential equation. It's dy over dx equals y times cosecant 2x. So it's cosecant 2x times y plus square root of tangent x, right? So recall that in order to find the integrating factor, we do e to the power of integral px dx. So in our case, our p of x is going to be cosecant 2x, right? Or actually, if you were to write this here, we would actually write this as, so actually, I guess we could just write this on the same side here, like. So we could have dy over dx minus cosecant 2x times y equals square root of tangent x. Okay. So in that case, our integrating factor is e to the power of integral negative cosecant 2x. And if we were to do that, so that would be cosecant 2x. So we'd have 1/2 here. So you can use your trigonometric identities to find what the integral of cosecant is, but that should give you like ln of cotangent. So if we were to quickly look at our formula booklet, we see that this should give us 1/2 ln cotangent x. Okay, so this is what we would get for our integration factor, or that would just be e to the power of ln square root of cotangent x, or it would just be square root of cotangent x. So this would be using properties of logs and exponents, right? So that would be our integrating factor. Okay. If you want to check why this differentiates into this one, you could refer back to part B, right? So we showed that 1/2 ln cotangent x differentiates into negative cosecant 2x. So it's kind of like a hence thing. If you want to integrate this thing, we use part B. Right? So we can say this is e to the power of 1/2 ln cotangent x. Okay, so D. Hence, by solving this differential equation, let's show that y is x square root tangent x. So since we found the integrating factor, we may as well just multiply it here. So we could do root cotangent x times dy over dx minus cosecant 2x times y times square root of cotangent x and square root of tangent x times cotangent x. So if you multiply tangent and cotangent, that's just going to be a 1. So square root of 1, we'll just write this as 1. Okay, now this one, we can recognize a chain rule going on, product rule going on. So we would have y prime and just the y here. So it seems to be like y times square root of cotangent x multiplied as is. Right? Because we don't differentiate square root of cotangent x. Here we differentiate square root of cotangent x because if you recall, differentiating square root of cotangent x to the power of 1/2, that should give you 1/2 to the power of cotangent x negative 1/2, and then we'd have negative cosecant squared x. Or we could, so simplifying that would just give us cosecant negative. So if you're trying to differentiate 1/2 here, so if you're trying to just differentiate cotangent x square root of that, that would give us this right here, and it would simplify into negative cosecant 2x. Okay. So that would be equal to 1, and that means y times square root of cotangent x is going to equal to x plus c. And if you want to find c, we could put in x equals pi over 4, y equals pi over 4. So pi over 4 times square root of cotangent pi over 4, that equals pi over 4 plus c. Cotangent pi over 4, that's just going to be 1, so c would equal 0. So if you were to solve for y, we would just get y square root of cotangent x is x. So that means y is going to be x over square root cotangent x, or just x root tangent x. Okay, so that's how you would do part D. And finally, let's move on to E. So we're now considering this curve. Y is x square root tangent x for x between 0 and pi over 2, right? Okay, so the actual y coordinate, if you were to use x is 5 pi over 12, let's find that. So we can plug this into our calculator, right? So 5 pi over 12 times square root of tangent 5 pi over 12. Make sure we were working in radians. Okay, so that gives us 2.52878 or 88, but this rounds to 2.53. So I believe earlier we had gotten y is 1.98. So that might be a bit off, right? So previously we said y was 1.98 according to Euler's method. So according to Euler's method, y was 1.98, but when we actually solve this differential equation and find the actual value of y, it turns out to be 2.53. So it is slightly different. So let's think about why. So Euler's method does often diverge from the actual thing in cases where the gradient might be changing rapidly, right? So for instance, in Euler's method, we assumed that this trend would continue. That's probably why we thought, if x increases by this much, y should increase by this much. But actually, the true y value was here. So why does it not give a good approximation? We would just say there's a substantial change in the gradient. So we could have overestimated or underestimated. So usually when it's concave down, we would end up overestimating. So this would be like the overestimate. But in our case, we underestimated it, right, with Euler's method. So we would expect this to be concave down, right? So this approximation is less than the y-coordinate. So Euler's method underestimates because the graph seems to be concave down, or we could just show how d squared y over dx squared is less than, or would be greater than 0. Right? So because we have a concave down shape, this approximation is less, not more. Finally, we have f. We're considering dy over dx minus y cosecant 2x is root tangent x. So how can you deduce that this has a positive gradient? Okay, so if you look at dy over dx, that's the slope function. That's like y cosecant 2x plus square root of tangent x. So for the given interval of x being between 0 and pi over 2, we could say that tangent x is going to be greater than 0. So square root of tangent x is also greater than 0. And cosecant, so 1 over sine 2x, right? So 2x is going to be between 0 and pi, right? So this is also going to be positive. So since both of these two terms are positive, we would say that dy over dx is going to be positive, right? So hence we have a positive gradient for x being between 0 and pi over 2. So there you have it. That's number 12. The question basically went like this. We initially used Euler's method and our calculators to just find what our y value is for a certain value of x. But then we also found, we also solved the differential equation manually, right? Using the integrating factor. So the question kind of guides you along the way. And then you compare your results from the numerical Euler's method versus your analytical, like hand manually solved method, right? And then you comment on why the discrepancy existed. And then you talk about, in the final one, like how the slope is always positive. Yep, so that's it for this paper.